Welcome to lecture series on digital electronics under EPG Pathshala. Logic gates are the basic building blocks of all digital electronic systems. Boolean algebra helps the digital system designer to simplify the logic expressions. The visualization technique with the help of K-maps can help you in analyzing and designing the circuit in a graphical method. In addition to that, we will be studying different logic circuits which are more complex and used in many applications. So, for example, we will be studying combinational and sequential circuits. Combinational circuits are the one wherein the output is dependent upon only present input conditions, whereas in case of sequential circuit, to decide the output, the designer must take care of considering its past input as well as the present input. Combinational circuits are classified into three categories. One, digital processing circuits, data transfer circuits, and the third one is a code converter. In this module, we will be focusing more on the designing and analysis of combinational circuits. Then the focus is more on understanding the basic principles of comparator. We will classify the comparator into two types, identity comparator and the magnitude comparator. The identity comparators and magnitude comparators are used in simple applications like arithmetic circuits, designing ALU, that is arithmetic and logical unit. In addition to that, many microprocessors and microcontrollers requires comparator block to make certain decisions. It is also used in industrial process control, servo motor control and so on. Let us begin the journey of combinational circuit with the help of the simplest circuit, that is comparator. Let us now get familiar with the learning objectives of this session. Initially, we shall learn the basic concepts of combinational circuits. After getting familiar with time independent circuit, that is combinational circuit, we will focus it on the classification scheme of combinational circuits. A simple procedure to design a combinational circuit will also be introduced. The knowledge of designing the combinational circuit will be used for comparator. Comparator is one of the important circuit in building today's most popular ALU, microprocessor and microcontroller ICs. Digital circuits are designed using principles of Boolean algebra and simple logic gates. Digital circuits are classified into two main categories, that is combinational and sequential circuits. This classification is based on the nature of the outputs. In combinational circuit, the output is function of present inputs only. The output is independent of previous inputs and outputs. In sequential logic, the output is a function of both present and past input conditions. Combinational logic refers to the logic circuit whose output is a function of the present value of inputs only. Sometimes it is also referred to as a time independent logic circuit. In combinational circuit, the circuit is constructed using different logic gates. A combinational circuit can have n number of inputs and m outputs. The output of this circuit at any instant of time depends on the logic levels present at the input terminals. The combinational circuits do not use any memory. The previous state of the input does not have any effect on the present state of the circuit. Let us take a real life example of combinational circuit, car security system. In this example, the siren is turned on when the master switch is on and someone opens the door. As soon as someone opens the door, the siren is turned on, which is shown as a blinking. If you close the door, then the siren will turn off immediately. With this setup, the output, which is the siren, is depend only on the present inputs, which are the master and door switches. Once the master and door switches are closed, the car will now start moving. A combinational circuit consists of input variables, logic gates and output variables. The logic gates accepts signals from the inputs and generate the signals to the output. This process transforms binary information from given input data to the required output data. Obviously, both input and output data are represented by binary signals. That is, they exist in two possible values, one representing logic 1 and the other is logic 0. Combinational circuits are made of basic logic gates and or NOT, as well as using universal logic gates and XOR gates. These gates are combined or connected together to produce more complicated logic circuits. These logic gates are the building blocks of combinational logic circuit. For n input variables, there are 2n possible combinations of binary input values. For each possible input combination, there is one and only one possible output combination. A combinational circuit can be described by m Boolean functions, one for each output variable. Each output function is expressed in terms of the n input variables. Let us now talk about the types of combinational circuits. There are three major types of combinational circuits: data processing circuits that processes or transforms the data. Data transfer circuits are normally used to control the flow of logic. Code converters are preferred for conversion from binary to any other code and vice versa. Adder, subtractor, comparator, multiplier, parity generators and checker circuits are few examples of data processing circuits. Multiplexer, demultiplexer, encoder, decoder are few examples of data transfer circuits, whereas code converters include binary to BCD, to Gray 7-segment code and vice versa. For the design of combinational circuit, basic logic gates and derived logic gates are preferred. The design of combinational circuit begins with problem definition and ends with logic circuit or set of Boolean expressions. Let us now understand the design procedure. Step number 1, state the problem clearly. Here we need to understand the problem with the specific inputs and outputs. From the given problem, let us determine the available input and required output variables from the given problem. Assign a letter symbol to each input and output variable of the circuit. Derive the truth table that relates the input and output parameters. With the number of inputs, say n, we can get definitely 2n different possible combinations. Each combination represents a row in the truth table. After preparing the truth table, the next step is to write the Boolean functions for the output. Further, simplify the Boolean expression with the help of Boolean algebra to reduce the number of variables. Here we may take the help of Karnaugh maps as well. This is the last step in designing the combinational circuit, that is draw the logic diagram for the given problem. In many applications, logic diagram is available, but correlation between input and output parameters are unknown. The analysis of combinational circuit is the reverse process of the design. Let us now start with the analysis procedure. Step number 1, take a closer look at given combinational circuit. Identify the available inputs and outputs and label them appropriately. Find the output Boolean function for each logic gate. Obtain the Boolean functions and prepare the truth table for the given circuit in terms of input variables. Thus, the 4-step process can help us in analyzing the combinational circuit. Comparator is a combinational logic circuit that compares two binary quantities and produces outputs which determines the relationship between two binary numbers. An exclusive OR gate can be used as a basic comparator. Digital comparators are also called as binary or logic comparators. Comparator is a very useful combinational circuit capable of comparing two numbers as input in binary form and determines whether one number is greater than, less than or equal to other number. This logic circuit is used for testing whether the binary number at one input can be greater, less or equal to another binary numbers. There are two types of comparators: equality comparator and magnitude comparator. Let us now discuss the equality or identity comparator. A and B are two input binary numbers and there is only one output, indicating whether the input numbers are equal or not. Output is active when both the inputs are equal, that is, A is equal to B is equal to 1. Similarly, output is active when both the inputs are equal, that is 0. Otherwise, the output of the logic circuit is inactive. Let us study 1-bit equality comparator using simple XOR circuit. The truth table of XOR indicates the operation of identity or equality comparator. We have two numbers which are 1 bit each. A and B can have 4 possible combinations: 0 0, 0 1, 1 0 and 1 1. This XOR gate acts as an active low comparator. The output Y is low if both A is equal to B is equal to 0 or A is equal to B equal to 1. Let us study active high 1-bit equality comparator using simple XNOR circuit. The truth table of XNOR indicates the operation of identity or equality comparator. The truth table once again will have 4 possible combinations and the output Y is high only when both inputs A and B are equal. So, thus we have active high comparator. 2-bit binary numbers A and B can be represented as A1 A0 and B1 B0, where A1 and B1 are the most significant bits and A0 and B0 are the least significant bits of the numbers a and b respectively. A1 is compared with B1 and A0 is compared with B0. If A1 is equal to B1 and A0 is equal to B0, output of 2-bit comparators will be high. If A1 is not equal to B1 or A0 is not equal to B0, the output will be low. So, thus we can have some Boolean expression derived from this. Let us study the truth table of 2-bit equality comparator. In the truth table, we have 4 inputs, 2 inputs per the binary number A1, A0, B1, B0, and the output of the comparator is Y. If you consider 4 inputs for a comparator, we can have 2 raised to 4, that is 16 possible combinations, and these 16 possible combinations are written in natural binary sequence from 0000 to 1111 in a increasing order. The output of the 2-bit equality comparator is high only when both the numbers A and B are equal. Otherwise, the output of the comparator is 0. From this, we can write a Boolean expression y is equal to complement of A0 XORed with B0 and complement of A1 XORed with B1. Thus, you can definitely see any comparator can be constructed using either XOR or XNOR depending upon whether it is active high or active low comparator. Let us now study another type of comparator, that is magnitude comparator. This magnitude comparator as compared to identity comparator has 3 outputs. It has 2 inputs A and B, but the outputs are 3: A greater than B, A equal to B and A less than B. But note one important thing, that only one output is active at a time. In equality comparator, we have only one output A equal to B, which could be active or inactive. 1-bit magnitude comparator. Now, this is the simplest case of magnitude comparator, wherein we need to compare 1-bit binary number. Let us say A and B are the 1-bit binary numbers, and the outputs of this magnitude comparator could be A greater than B, A equal to B or A less than B. Let us prepare the truth table for 1-bit magnitude comparator. There are 2 inputs A and B, each one are 1-bit inputs, and there are 3 outputs. In the truth table, let us write all input possible combinations 00, 01, 10 and 11. Now, let us determine the output for each condition. For the first condition, when both A and B are 0, definitely the output A equal to B is 1 and other outputs are 0. In the second condition, when A is 0 and B is 1, this simply indicates A is less than B. Naturally, the A less than B output is high and other 2 outputs are low. In the third condition, when A is 1 and B is 0, A greater than B output is high and other 2 outputs are low. And in the last condition, when both A and B are 1, 1, the second output, that is A is equal to B, is active and other 2 outputs are 0. It is very easy to derive Boolean expression from the truth table by visual inspection. The Boolean expression could be obtained for each of these outputs. Let us say for A greater than B, we have output A dot B bar. For A equal to B, the output will be A XOR B and its complement, that is XNOR gate. And for the third output A less than B, the output will be A bar dot B. Let us now prepare the logic diagram for 1 bit magnitude comparator. Looking at the three expressions, we can definitely see that XNOR gate will provide the equality and two AND gates along with inverters will provide the remaining two outputs. So, in the figure, one AND gate has input A and B bar, whereas A less than B has input A bar B, whereas XNOR gate will provide the third output A equal to B. Let us now begin with the 2-bit magnitude comparator. The knowledge that we have acquired in 1-bit magnitude comparator can be used in this case. Let us consider two binary numbers A and B. Each of them will have 2 bits. Those are to be compared in this comparator. Let us consider A is represented by A1, A0 and B number is represented by B1 and B0, whereas A1 and B1 represents the MSB, A0, B0 represents the LSB, and we need to compare each one of these bits in case of magnitude comparator. So, let us consider a circuit wherein we have 4 inputs and 3 outputs. These 4 inputs are corresponding to A1 A0 and B1 B0 for 2 binary numbers, and the 3 outputs are A less than B, A greater than B and A equal to B. So, let us understand the design procedure for this 2-bit magnitude comparator. Let us prepare the truth table for 2-bit magnitude comparator. For this comparator, there are 4 inputs A1, A0, B1, B0, and the outputs are A greater than B, A equal to B and A less than B. With these 4 inputs, we can have 2 raised to 4, that is 16 possible combinations. These combinations will start from all bits 0 and will go through the natural binary increment sequence to 1 1 1 1. Let us now prepare the K-map for one of the output, let us say A greater than B. It is a K-map of 4 variables. Naturally, A forms the row and B forms the column. Let us map the ones those are present in the output column A greater than B. So, we have 6 cells which are ones on the K-map. From this, it is clear that we can form a group of 4 cells which is a chord, and this chord definitely eliminates 2 variables out of 4. These are given by a Boolean expression. Let us now talk about the first product term, which is simplified using K-map. This product term is A1 B1 bar, eliminating the A0 and B0. Let us now write the Boolean expression for the remaining ones. The product term for this cell which is marked by red is A1 bar A0, B1 bar B0 bar. The next product term for the remaining one is A1 A0, B1 B0 bar. Let us now simplify this Boolean expression. From the last 2 product terms, we can take A0, B0 bar common. So, thus we have an expression for A greater than B in a simplified form as A1 B1 bar OR with A0 B0 bar and Y1. Y1 is basically the term that we have introduced to represent XNOR gate. Let us now prepare a K-map for the second column A equal to B. Once again, we can start mapping the ones on the K-map. For the one which we have placed on the K-map, the Boolean product term is A1 bar A0 bar B1 bar B0 bar. The second one that we have placed produces a product term A1 bar A0 B1 bar B0. The third one that we have placed in the K-map provides A1 A0 B1 B0, and the last one that we have placed here produces A1 A0 bar B1 B0 bar. Let us simplify this Boolean expression such that we can get two product terms. These two product terms basically of sums. These two are represented by the product of y1 and y0, and each y term represents the expression for XNOR. Let us now prepare a K-map for A less than B, and let us put the ones which are present in that column on the K-map. There are 6 ones, those are present in the truth table, are also mapped on the K-map. Out of these 6 ones, we can definitely form a group of 4 cells as marked here. This group is a chord. Naturally, in a chord we can eliminate 2 variables. So, thus the reduced product term is of A1 bar and B1. Let us write the product term of the cell which cannot be further simplified as A1 bar A0 bar B1 bar B0. Let us write now the product term for the remaining cell, that is A1 A0 bar B1 B0. With these 4 variables, we can now simplify the Boolean expressions by taking 2 product terms common from last product terms, which is shown here. The final expression for A less than B is equal to A1 bar B1 bar OR with A0 bar B0 and Y1, where Y1 once again represents the expression for XNOR gate. Let us now prepare the logic diagram from the Boolean expressions. The logic expression for A equal to B is shown here, which can be represented by 2 XNOR gates and 1 AND gate. Similarly, A greater than B can be prepared using 3 NAND gates, because 2 NAND gates will provide or will cancel the complement. The Boolean expression for A greater than B can be converted into the logic diagram with the help of 3 NAND gates as shown here. One of the NAND gate receives one of the input from XNOR. We can even represent the Boolean expression for A less than B using logic diagram, which could be prepared using 3 NAND gates as shown here. So, thus with the help of 3 Boolean expressions, we can obtain the logic diagram for 2-bit magnitude comparator. Let us now begin with 4-bit magnitude comparator. This 4-bit magnitude comparator can be used to compare 4-bit words. The 2 4-bit numbers are A is equal to A3, A2, A1, A0, and B3, B2, B1, B0, where A3 and B3 are the most significant bits. It compares each of these bits in one number with the bits in that of the other number and produces one of the following outputs as A equal to B, A less than B, or A greater than B. Let us now think about the truth table for 4-bit magnitude comparator. Looking at the 4-bit words, effectively if you see, there are 4 plus 4, that is total 8 bits at the input, which naturally will give you a truth table consisting of 2 raised to 8, that is 256 possible input conditions, which is impossible to plot. So, best way, let us now think in a different way and prepare a truth table which will give you limited number of conditions. This truth table contains 4 input groups, each corresponding to the binary numbers from each MSB or LSB positions. Let us consider the first column in the input. It is a group which compares A3 and B3, second column compares A2 with B2, the third column compares A1 with B1, and the fourth column compares A0 and B0. So, in all, if it is observed that any of these numbers are greater or less or equal, naturally that is reflected on 3 outputs. Here we will consider the output logic statement for this magnitude comparator. If A3 is 1 and B3 is 0, then A is greater than B irrespective of the other input groups. When A3 is less than B, irrespective of other input groups, definitely the output A less than B is active. When A3 is equal to B3, naturally the comparison should be made for the next higher order bit, that is A2 greater than B2 irrespective of other 2 groups. If this is true, then A is greater than B. When A3 is equal to B3 and A2 less than B2, then irrespective of other 2 input groups, the output A less than B is active. When A3 is equal to B3 as well as A2 is equal to B2 and A1 is greater than B1, then the output A greater than B is high. When A3 is equal to B3, A2 is equal to B2, A1 less than B1 and irrespective of A0 B0 group, definitely the output A less than B is high. When A3 is equal to B3, A2 is also equal to B2, A1 is also equal to B1, the next step is let us check whether A0 is greater than B0. Now, in this case if A0 is greater than B0, definitely the output A greater than B is high. When A3 is equal to B3, A2 is equal to B2, A1 is equal to B1 and A0 is less than B0, in this case definitely the output A less than B is active. And finally, the last case in the truth table, when all 4 inputs are equal. In this case the output A is equal to B is high. Now, with this truth table, let us now prepare the expression for the outputs. The 3 outputs can be considered for generating the magnitude of the 2 input numbers A and B. The inputs are 4-bit numbers and the outputs are A greater than B, A less than B and A equal to B. Now, for each bit let us consider Si is equal to Ai and Bi or with Ai bar and with Bi bar is equal to complement of AI BI bar or with AI and BI. The S input is true when both A and B are true. For A is equal to B, let us obtain the Boolean expression. A3 is equal to B3, A2 is equal to B2, A1 is equal to B1 and A0 is equal to B0. This is the only one condition which is generating output Y A is equal to B. Here we can write 4 terms represented as S3, S2, S1 and S0, and these terms are basically indicating some kind of XNOR gate, indicating its equality comparator. The equal output is produced when all the individual bits of one number are exactly coincides with the corresponding bits of another number. Let us now prepare the logic expression for A greater than B. For A greater than B, there are 4 cases. A3 B3 is 1 0, A2 A1 A0 and B2 B1 B0 can be anything. So, naturally we can say A is equal to 1 XXX and B is equal to 0 XXX, where X is unknown condition. Second case is when A3 is equal to B3 and A2 B2 is 1 0 and A1 A0 and B1 B0 can be anything. So, we have the second case. The third case is A3 is equal to B3, A2 is equal to B2 and A1 B1 is equal to 1 0 and A0 B0 is XX. And the last case is when A3 is equal to B3, A2 is equal to B2 and A1 is equal to B1 and A0 B0 is 1 0. So, for example, the number could be A is equal to 1011 and B is equal to 1010. So, thus we can get the logic expression for the output A greater than B consisting of 4 product terms as indicated here. Similarly, we can obtain the logical expression for A less than B. Once again here there are 4 possible cases and each one of these possible case can produce a product term which is indicated in the final expression Y as sum of 4 product terms. So, thus we can obtain 3 Boolean expressions for 4-bit magnitude comparator, which is shown in this slide. So far we have discussed the discrete equality or magnitude comparators, how these could be designed and constructed. There is a standard IC 7485 under TTL series which compares 2 unsigned 4-bit binary numbers. The unsigned numbers are A3, A2, A1, A0 forms one binary number X and the second binary number Y is represented by B3, B2, B1 and B0. In addition to that, this 4-bit magnitude comparator has 3 cascaded inputs. These 3 cascaded inputs are input for A less than B, A greater than B and A equal to B. So, these 3 possible groups of inputs are considered to generate the comparator output A equal to B, A less than B and A greater than B. This IC 7485 can be used for cascading purpose. Cascading inputs provide a means for expanding the comparison operation to more than 4 bits by cascading 2 or more 4-bit comparators. When 2 comparators are to be cascaded, the outputs of lower order comparator are connected to corresponding inputs of the higher order comparator. the comparator on left is comparing lower 4 bits and right comparator compares the higher order nibble. Higher order comparator compares its inputs and produces the output regardless of what inputs are applied to its cascade inputs from lower order comparator. Once the higher order comparator compares the difference in the higher order bits, it generates the corresponding output, which could be A greater than B, less than B or equal to B. Let us now look at the applications of the comparators. Comparators are popularly used in arithmetic and logical circuits. In ALU, it is normally used for comparing two binary numbers. Similarly, these two binary numbers can be compared in the standard microprocessors and microcontrollers or computers for interfacing external devices. Another application for comparator is analog to digital converter, where the analog input, once it is converted to digital, before it could go to the next conversion, can be compared. Similarly, the comparator can find applications in process control applications or servo motor control. In process control, one can compare the set temperature, which is represented in binary form, and the measured temperature measured from the sensor. In servo motor control, once the set position or angle is set, one can definitely compare whether the given angle is set or not. Here once again the comparator plays an important role. And the last application, but not the least, we can use comparators for password verification, biometric applications, for searching and surfing the BCD numbers. Let us now summarize the things that we have studied in this module. Combinational circuit is the circuit which provides an output which is dependent on only present input conditions. Combinational circuits are classified into three categories: data processing circuit, data transfer circuit and code converters. In addition to that, the combinational circuits are divided into two types. The first one, that is equality comparator, and second one is magnitude comparator. Equality comparator has two inputs and one output, whereas the magnitude comparator has two inputs, but the outputs are three. These outputs are A less than B, A equal to B and A greater than B. In this module, you also learned the design and analysis process of the combinational circuits. The applications of the combinational circuits, specifically the comparator, are ALU, microprocessor and microcontrollers. We can even use these comparators for industrial process control, servo motors and comparing or matching the sequences. With this, we conclude in this session and will meet in the next session. Thank you.